A tiltrotor is an aircraft which generates lift and propulsion by way of one or more powered rotors mounted on rotating engine pods or nacelles, usually at the ends of a fixed wing, or an engine mounted in the fuselage with drive shafts transferring power to rotor assemblies mounted on the wingtips. It combines the vertical lift capability of a helicopter with the speed and range of a conventional fixed-wing aircraft. For vertical flight, the rotors are angled so the plane of rotation is horizontal, lifting the way a helicopter rotor does. As the aircraft gains speed, the rotors are progressively tilted forward, with the plane of rotation eventually becoming vertical. In this mode, the wing provides the lift, and the rotor provides thrust as a propeller. Since the rotors can be configured to be more efficient for propulsion and it avoids a helicopter's issues of retreating blade stall, the tiltrotor can achieve higher speeds than helicopters. A tiltrotor aircraft differs from a tiltwing in that only the rotor pivots rather than the entire wing. This method trades off efficiency in vertical flight for efficiency in STOL/STOVL operations. History. The idea of constructing vertical takeoff and landing aircraft using helicopter-like rotors at the wingtips originated in the 1930s. The first design resembling modern tiltrotors was patented by George Lieberger in May 1930, but he did not further develop the concept. In World War II, a German prototype, the Fock-Achilles FAR 269, was developed starting in 1942, but never flew. Two prototypes which made it to flight were the one-seat Transcendental Model 1G and two-seat Transcendental Model 2, both powered by single reciprocating engines. Development started on the Model 1G in 1947, though it did not fly until 1954. The Model 1G flew for about a year until a crash in Chesapeake Bay on July 20, 1955, destroying the prototype aircraft but not seriously injuring the pilot. The Model 2 was developed and flew shortly afterwards, but the U.S. Air Force withdrew funding in favor of the Bell 15-3 and it did not fly much beyond hover tests. The Transcendental 1G is the first tiltrotor aircraft to have flown and accomplished most of a helicopter-to-aircraft transition in flight. Built in 1953, the experimental Bell 15-3 flew until 1966, proving the fundamental soundness of the tiltrotor concept and gathering data about technical improvements needed for future designs. A related technology development is the tiltwing. Although two designs, the Canada CL-84 Denarvit and the LTVX C-142, were technical successes, neither entered production due to other issues. Tiltrotors generally have better hover efficiency than tiltwings, but less than helicopters. In 1968, Westland Aircraft displayed their own designs, a small experimental craft and a 68-seater transport WO-28 at the SBAC Farnborough Air Show. In 1972, with funding from NASA and the U.S. Army, Bell Helicopter Textron started development of the 1515, a twin-engine tiltrotor research aircraft. Two aircraft were built to prove the tiltrotor design and explore the operational flight envelope for military and civil applications. In 1981, using experience gained from the 15-3 and 15-15, Bell and Boeing Helicopters began developing the V-22 Osprey, a twin-turboshaft military tiltrotor aircraft for the U.S. Air Force and the U.S. Marine Corps. Bell teamed with Boeing in developing a commercial tiltrotor, but Boeing went out in 1998 and Augusta came in for the Bell Augusta BA-609. This aircraft was redesignated as the AW609 following the transfer of full ownership to AgustaWestland in 2011. Bell has also developed a tiltrotor unmanned aerial vehicle, the TR-918 Eagle Eye. Russia has had a few tiltrotor projects, mostly unmanned such as the Mil-Me-30, and has started another in 2015. Around 2005 or 2010, Bell and Boeing teamed up again to perform a conceptual study of a larger quad-tilt rotor for the U.S. Army's Joint Heavy Lift program. The QTR is a larger, four-rotor version of the V-22 with two tandem wings, sets of fixed wings and four tilting rotors. In January 2013, the FAA defined U.S. tiltrotor noise rules to comply with ICAO rules. A noise certification will cost $588,000, same as for a large helicopter. Eggers-Storsland says they have free-flown a manned electric tiltrotor in 2013 called Project Zero, with its rotors inside the wingspan. In 2013, Bell Helicopter CEO John Garrison responded to Boeing's taking a different airframe partner for the U.S. Army's future lift requirements by indicating that Bell would take the lead itself in developing the Bell V-280 Valor, with Lockheed Martin. In 2014, the Clean Sky 2 program awarded Eggers-Storsland and its partners $328 million to develop a next-generation civil tiltrotor design for the offshore market, with critical design review near the end of 2016. The goals are tilting wing sections, 11 tons maximum takeoff weight, seating for 19 to 22 passengers, first flight in 2021, a cruise speed of 300 knots, a top speed of 330 knots, a ceiling of 25,000 feet, and a range of 500 nautical miles. Technical considerations. Controls. In vertical flight, the tiltrotor uses controls very similar to a twin or tandem rotor helicopter. Yaw is controlled by tilting its rotors in opposite directions. Roll is provided through differential power or thrust. Pitch is provided through rotor cyclic or nacelle tilt. Vertical motion is controlled with conventional rotor blade pitch and either a conventional helicopter collective control lever or a unique control similar to a fixed-wing engine control called a thrust control lever. Speed and payload issues. The tiltrotor's advantage is significantly greater speed than a helicopter. In a helicopter, the maximum forward speed is defined by the turn speed of the rotor. At some point the helicopter will be moving forward at the same speed as the spinning of the backwards moving side of the rotor, so that side of the rotor sees zero or negative airspeed, and begins to stall. This limits modern helicopters to cruise speeds of about 150 knots/277 km per hour. However, with the tiltrotor this problem is avoided, because the proprotors are perpendicular to the motion in the high-speed portions of the flight regime, meaning that the tiltrotor has relatively high maximum speed over 300 knots/560 km per hour has been demonstrated in the two types of tiltrotors flown so far, and cruise speeds of 250 knots/460 km per hour are achieved. This speed is achieved somewhat at the expense of payload. As a result of this reduced payload, some estimate that a tiltrotor does not exceed the transport efficiency of a helicopter, while others conclude the opposite. Additionally, the tiltrotor propulsion system is more complex than a conventional helicopter due to the large, articulated nacelles and the added wing. However, the improved cruise efficiency and speed improvement over helicopters is significant in certain uses. Speed and, more importantly, the benefit to overall response time is the principal virtue sought by the military forces that are using the tiltrotor. Tiltrotors are inherently less noisy in forward flight than helicopters. This, combined with their increased speed, is expected to improve their utility in populated areas for commercial uses and reduce the threat of detection for military uses. Tiltrotors, however, are typically as loud as equally sized helicopters in hovering flight. Noise simulations for a 90-passenger tiltrotor indicate lower cruise noise inside the cabin than a Bombardier Dash 8 airplane, although low-frequency vibrations may be higher. Tiltrotors also provide substantially greater cruise altitude capability than helicopters. Tiltrotors can easily reach 6,000 m/20,000 feet or more, whereas helicopters typically do not exceed 3,000 m/10,000 feet altitude. This feature will mean that some uses that have been commonly considered only for fixed-wing aircraft can now be supported with tiltrotors without need of a runway. A drawback, however, is that a tiltrotor suffers considerably reduced payload when taking off from high altitude. Monotiltrotor. A monotiltrotor aircraft uses a tiltable rotating propeller, or coaxial proprotor, for lift and propulsion. For vertical flight, the proprotor is angled to direct its thrust downwards, providing lift. In this mode of operation, the craft is essentially identical to a helicopter. As the craft gains speed, the coaxial proprotor is slowly tilted forward, with the blades eventually becoming perpendicular to the ground. In this mode, the wing provides the lift, and the wing's greater efficiency helps the tiltrotor achieve its high speed. In this mode, the craft is essentially a turboprop aircraft. A mono-tiltrotor aircraft is different from a conventional tiltrotor in which the proprotors are mounted to the wingtips, in that the coaxial proprotor is mounted to the aircraft's fuselage. As a result of this structural efficiency, a mono-tiltrotor exceeds the transport efficiency of both a helicopter and a conventional tiltrotor. One design study concluded that if the mono-tiltrotor could be technically realized, it would be half the size, one-third the weight, and nearly twice as fast as a helicopter. In vertical flight, the mono-tiltrotor uses controls very similar to a coaxial helicopter, such as the Kamoth Ka-50. Yaw is controlled for instance by increasing the lift on the upper proprotor while decreasing the lift on the lower proprotor. Roll and pitch are provided through rotor cyclic. Vertical motion is controlled with conventional rotor blade pitch. List of tiltrotor aircraft. Edgar Stoursland AW609, Edgar Stoursland Project Zero, American Dynamics AD150, Bell 15-3, Bell 15-15, Bell Eagle Eye, Bell Boeing V-22 Osprey, Curtiss-Wright X-19, Foch-Achilles FAR 269, IAI Panther, Bell V-280 Valor. See also, pitch drop back, tiltjet, tiltwing, tail sitter, VTOL, thrust vectoring. References. External links, First Motorized Tiltrotor, Tiltrotor and the Future, independent 60-minute documentary video on technological development of tiltrotor technology.